Question before final tweet.
Last
Like the one
year I
part.
got a question right there.
Get the one part.
Do you microwave your tea?
Yeah.
All right. So, if I sound weird today, it's because I have a sore throat. So hopefully I won't talk my voice dead. So what we're gonna do today is you can think of this as sort of a culminating lecture. The stuff we're gonna talk about today is not stuff I'm gonna test you on because I haven't given you homework on it, but it's the beginning of what the rest of your sort of life as an applied mathematician or engineer will look like. So I'm going to talk about connections between physical equations, phase plane, and the way that we use eigenvalues and eigenvectors to analyze linear and nonlinear differential equations. Right? So if I had more time, if I had 3 more weeks of this is what we'd spend the next 3 weeks doing, is talking about nonlinear systems. So the first thing, and this came up in the last class, the first thing I need to point out is there's a case of linear systems that I did not do that I think I should, which is if you had a matrix equation that looked like x prime is equal to ax, and it turned out that the eigenvectors for the eigenvalues lambda were of the form a plus ib. So I showed you that if you had lambda 1 with vector v1 and lambda 2 with vector v2, and this stuff was all real, if everything over here is real, then the solutions look like x is c1e to the lambda 1t v1 plus c2e to the lambda 2t v2. So we did that. What I didn't show you is what to do when you have a complex eigenvalue and complex eigenvectors. So imagine here you've got vector v1 and then v1 complex conjugates. Remember that like the 2 vectors are related by taking complex conjugates. In this case, what you do is you set up a solution x1 by taking the real part. So you basically multiply everything out, and everything without an I in it, you sort of glom it together into a solution that looks like this. And then x2 is the imaginary part of that vector. So this will turn out, because this is made of sines and cosines, you should expect that what happens here is you get sines and cosines, sums of sines and cosines. And the curves that you get from solving an equation that has complex eigenvalues tend to either look like spirals out, spirals in, or circles, like ellipses, right? So if the A is positive, it means you're exponentially expanding. If the A is negative, it means you're pulling in. And if there is no A and it's just imaginary, that means you're on some kind of circle. This is, I'm going to talk about this again. This is like A positive, this is A negative, and this is A equal to 0. Okay, so I'm not going to expect you to be able to compute solutions to these things. I just want you to know that this is going to come up as an example that we're going to do today, and I want you to know that if we get complex eigenvalues, that we're looking at circular behavior in the system of solutions. Let me not blow up. All right, so I want to start by connecting up. I want to talk about the phase plane today, and I want to make a more concrete connection to the phase plane. So let's look at this differential equation. X prime prime plus 4x is equal to 0. So that is an undamped mass spring system. The method of solution for this spring system was we wrote down m squared plus 4 is equal to 0. That's the characteristic polynomial, auxiliary polynomial. And we solve it to get m is equal to plus or minus 2i. And then from there, we leap to the conclusion that the solutions to this thing look like x of t is equal to c1 cosine of 2t plus c2 sine of 2t. And if I further add in some initial conditions, like x of 0 is equal to 0, and x prime of 0 is equal to 1, so I'd say, let's do it the other way, 1 and 0, you could solve the initial value problem. X of 0 is equal to c1 times 1 plus c2 times 0, and that's supposed to be equal to 1, so c1 must be 1. X prime of t is equal to minus 2c1 cosine of 2t plus 2c2 backwards. Sorry, sine 2t. 2c2 cosine of 2t. So x prime of 0 is equal to, okay, 0 plus 2c2, and that's all supposed to be equal to 0, and that implies that c2 is 0. So for that specific set of initial conditions, I know that the specific solution I get here is x of t is equal to cosine of 2t. That is the specific solution to that initial value problem. So what I want to do is look at that, what that looks like in the case where I turn it over into a linear system. And there's a really nice video on this on the phase plane if you want to look at it. So 3 blue, 1 brown is a really nice video on phase plane interpretations that I'm not following, but this is what made me think of this. So let's take that differential equation and turn it into a system and see what happens. So remember that when we're turning a linear equation into a system, we have to use a set of substitutions. I'm going to try to get the second derivatives out of this. So I'm going to make the substitution y is equal to x prime, and so therefore y prime will be x double prime. So that's my collection of substitutions. If I do that, I'm going to get the equation y is equal to x prime, and then this equation I'm going to try to get rid of the second derivatives. And I can do that by plugging in, everywhere I see an x double prime, I can stick in a y prime. So I get y prime plus 4x is 0. And if I want to put this in the standard form for a system, that would say x prime is equal to y, and y prime is equal to minus 4x. Or if I like to really emphasize the fact that I'm looking at a linear system, so the matrix form that I've gotten out here looks like this. X prime, y prime is equal to 0, 1, minus 4, 0 times xy. And if I look at the characteristic polynomial for this matrix A, so A is equal to 0, 1, minus 4, 0. It has characteristic polynomial, this maybe shouldn't be surprising to you, lambda squared plus 4. That's weird. The characteristic polynomial of the matrix and the auxiliary polynomial for the differential equation match, which is not a surprise. It's like it's not an accident, is what I should say. And so that means that our eigenvalues are plus or minus 2i, which is the same as the roots of the characteristic polynomial. Now, because these are complex eigenvalues, I know that my general solution to this equation looks something like this. X of t is equal to c1 times the real part of e to the minus 2i v1. I'm not going to find v1. Plus c2 times the imaginary part of e to the minus 2i v2, or sorry, v1. What I want you to imagine here is just these are sines and cosines, and I'm putting them inside vectors, so I get sums of sines or cosines in the entries. This will be a function, a parametric equation, where the x coordinate is a function of sines and cosines, and the y coordinate also has sines and cosines inside of it. If you actually plot what this does in the phase plane, you get this. So if you actually expressly wrote that solution down, and you went to the phase plane and wrote down what that looks like, that curve looks like this. Here's x, here's y, that curve travels this way. Now what I want to do is I want to imbue this solution, which looks like this. I want to imbue this solution with physical meaning. In a mass spring system, what does the x mean? This x right here, what does that stand for? What's that? No, x, just x. Sorry, I know I pointed x double prime. What does the x mean? Position from equilibrium, right? Up or down from equilibrium. So this is displacement from equilibrium, right? Or position relative equilibrium. So it's a position. What does the y measure in the system?
Velocity, it's x prime.
Yeah, see, the y variable is a variable that's tracking velocity. when I made this substitution, it's not a random algebraic substitution. I'm now looking at the relationship between position and velocity. When you get used to reading these diagrams, this actually has more information inside of it than this does. If you plot the solution over here, what you get looks like this. Oh, that is the way that the spring is actually oscillating, right? The mass is going up and down. This is the trajectory that the mass takes. It starts here and goes down and comes back up and goes down. But notice, that just tells me about position. It doesn't tell me about the velocity that the mass is traveling with. That would be contained in the derivative function. This picture, when I'm at that point right there in this picture, that's like being right here. My position is maximally away from 0, but my position is maximally away, but my velocity is nothing. I've reached the end of the chain. I've stopped. As this particle starts traveling this direction, what's happening is its position is getting back closer to equilibrium, but its velocity is increasing. At this position, if you back, so the image of this point on the x-axis, if that point would just be going back and forth like this, this motion back and forth on the x-axis would correspond to this motion up and down in this picture. But notice I get more information because it also records the velocity of the system as well. So this is tracking, oh, what happens right here? I'm at equilibrium in the x position. The spring has like returned to equilibrium, but it's moving pretty quickly with maximum velocity. As it continues and stretches out the other direction, so it heads this way, the spring starts to stretch, but also the velocity gets back down to 0 again. So reaching this position would say, now you're at the bottom. Velocity is 0, but position is maximally negative. So this picture, to somebody that knows how to read it, has more information inside of it than that one does. Because this just tells you position against time, and this tells you position against velocity. Yep. Yep. Yeah, in fact, we're going to use the Jacobian matrix later in this class too. I'm bringing back 241. It's coming back in, or 143. It's all coming together today. Eigenvalues, eigenvectors, the Jacobian matrix, like the first order solutions, all of it. So, what are the different initial conditions set up here? Well, if you distorted the spring less, then say you didn't impute any initial velocity. I start the spring right here. What does that say? That says I'm starting with this deflection in the x-axis with no velocity, right? I just take the spring, I stretch it that far, and I let it go. And the curve that it gets on looks like this. What if I stretch the spring and also put initial velocity in? Well, instead of having to solve some sort of differential equation to figure out what the coefficients have to be, I could just say, well, the initial condition here would be, I'm going to start right here. That stretch with this initial velocity, and there's the curve that I fall on. Each initial condition puts me on a different cycle that relates the velocity and position of the mass. So what we're going to look at today, more generally, is what sort of things can even happen in a picture like this? This one's pretty special because mass spring systems oscillate. So here's the very first modification we can make to this. And this is going to be a qualitative analysis. And then we'll move into a quantitative one in a bit. What would happen if I did the same thing but I put damping on the spring? What do you think should happen? Now, just physically, what happens if I have a damp spring?
Approach 0.
It sort of oscillates and then comes in, but it stops, right? It sort of oscillates less and less and less until it gets to 0. What does that look like? I saw a couple of you do it. What does it look like on the phase plane? It's going to spiral in, right? So if you have a damped spring system, oh, I'm not including no forcing in what I'm talking about. Yeah, so what we're doing right now basically requires that there are no, this analysis that we're doing requires that no t's show up. So these are called autonomous equations. There's no function of t. These are functions of t, but no actual t's are anywhere in this picture, right? So if you put a forcing function and all of a sudden there are t's, and this doesn't work the same way. So this is called autonomous system analysis that we're doing right now. So in a damp mass spring system, you would expect wherever you started, if again, this was position and this is velocity, and you start stretched out, well, what happens? It starts going back to equilibrium with a certain velocity, but it doesn't get as far when it goes out the other side, right? It's been damped. And as it comes around, it doesn't get as far, and it doesn't get as far. And so you end up with spiraling in behavior. So this is an example of what we're going to call a stable spiral. And that happens when your eigenvalues to the matrix that you get here, that corresponds to lambda having the form a plus or minus ib, where a is a negative number. If a is negative, you spiral in. Because a being negative corresponds to the existence of a term that looks like e to the at, the exponential part. This is the sort of oscillating part. This is the exponential part. If this is negative, e to the at goes to 0. Okay, now this isn't physically realistic, at least for a mass spring system. But what if you got eigenvalues? What if you had lambda is equal to a plus I or minus ib, where a is a positive number? So you're going to be at equilibrium somewhere. So you start here, and then the spring starts to oscillate, but every time it goes further. This is called an unstable spiral. And then the case that we started with, where we had lambda was equal to just plus or minus IB, where there is no A, those are the ones that look like circles. So this is called circular. That's not how you spell circular. Right, so when we have complex eigenvalues that show up for the matrix that determines the equation, we have 3 different behaviors in the solution. So the point of this is the eigenvalues of the matrix are what told us this behavior. Even if we don't know the specific solutions, I still know that this is happening. The eigenvalues look like this. I have circular behavior. The eigenvalues look like this. I have spiral, like things that are spiraling out. I have like eigenvalues look like this. I have spirals that are circling in. So what I want to look at next is what that looks like in the real case. All right, so to do this, let's look at our first idea here, which is what if we had a matrix, say ax prime is equal to ax, and I just tell you that I have a lambda 1. In fact, I'll give you an example here. How about lambda 1 is 1, lambda 2 is 2, v1 turned out to be, I don't know, 1, 0, and v2 was 1, 1. You solved some system. Those were the eigenvalues and eigenvectors of A. So you know that the general solution looks like c1 e to the t times 1, 0 plus c2 e to the 2t times 1, 1. Let's look at the phase plane here. So last time I showed you a picture where all the solutions were combinations of solutions that travel along lines dictated by these 2 vectors. There's a vector 1, 0, and there's a vector 1, 1. And every solution to this differential equation is a combination of solutions that are moving along these lines. How are they moving along those lines? If I am on the line dictated by the vector 1, 0, and time goes, so I start anywhere. Which direction do I go as time goes to infinity? Yeah, e to the t gets big as time goes on. So I go this way if I'm on that line. What if I was over here? What direction do I go? Yeah, that would be like a negative vector, but multiplied by a number that's getting very large, right? So if I have the vector minus 1, 0 multiplied by e to the billion, I'm way over here somewhere, right? So I am going this direction if I'm over here, and I'm going this direction if I'm going over here. How about the blue vector? Let's see. Along the direction 1, 1, but dictated with something that's going to infinity. So it looks like there's this special point in the middle. We're going to talk about that in a second. And every solution looks like it's being thrown away from that spot right where these curves cross each other. In fact, I'm going to guess that generally, from this picture, I can look at the solutions to this differential equation. I know from the picture that probably we're looking at things that go out like this, right? They have to head away. No matter what the motions are doing, these things have to be sailing away from the middle. From any initial point, they must be headed out to infinity. So the point 0, 0 in the middle, so 0, 0 is called an equilibrium point. And the reason it's called an equilibrium point is because if you put 0, 0 in over here, you get x prime is equal to the vector 0, 0. Right? I mean, a times 0, 0 is 0, 0. So the derivative at 0, 0 is nothing. You can't move. If your derivative in the x direction and your derivative in the y direction are both 0, you're not going nowhere. However, if you move even a little bit, from that point, you go flying away to infinity. So, unstable equilibrium, a classic example is somebody balancing something on their hand, right? So this is in unstable equilibrium when I have it straight up and down. But if it deviates at all from that, it won't move. If I get it perfect, it won't move. But if it moves at all, it falls. If it moves at all, it falls away, and the curve tells you the direction the solutions are falling away. Okay. So, what else can happen in the linear case? That's not so hard to see. So if I have eigenvalues that were both positive, the place where those lines cross, this 0, is going to throw things away. Other possibilities. What if lambda 1 was negative and lambda 2 is positive? And I'll use the same vectors here. So just v1 and v2. So here's v1. Here's v2. So now, along the curve v1, which was the vector 1, 0, I am headed in. Because the solution that corresponds to this looks like e to the minus t times 1, 0. As time goes to infinity, I come towards 0 instead. This one is still headed away. E to the 2t times 1, 1 goes to infinity as time goes on. So I'm traveling away from the point here. Now I'll use a word that should remind you of 241. This already should be reminding you of 241 when we did derivatives way back when. When we solve for critical points, this is basically what we were doing. So now, this point in the middle, which is the equilibrium point, is called a saddle point. Some solutions are attracted from this direction, and they're repelled in this direction. Students are repelled. The solutions that are, they might be. Students, geez, stop saying that. Solutions that are traveling the blue line are headed away as time goes to infinity, and on the pink line, they're coming in. So that means your initial behavior, whenever you start, is going to pull you in. So solutions look like this. If I start at a point, I get pulled in and then pushed out. I get pulled in and then pushed out. Pulled in and then pushed out. Pulled in and then pushed out. So the nature of the eigenvalues tells you about how all of the solutions are behaving. It divides the plane up into pieces where you can sort of get a feel for the general nature of the solutions. Why? I haven't done this very well because these are supposed to be asymptotic here. So notice what happens is as the pink line gets closer and closer and closer to the equilibrium position, these curves have to approach the blue line. All right, so what's the last case? The really boring one. The stable solution. So I did the unstable, and I did the saddle, and now let's do stable. If I have lambda 1 is negative and lambda 2 is also negative, so that would be like, I don't know, lambda 1 is -1, and lambda 2 is -2 with the same vectors, just for example. And you do the same exact picture again. In this case, everything is being pulled in. And you've got what's called a stable equilibrium. Here, no matter where you start, you're going to the origin. I have some pictures of what this looks like that I'll post, I'll stick up on the books. The first one was unstable. I said it, but I didn't write it down. Yeah, when all the solutions are being thrown away, it's unstable. When all the solutions are being pulled into this special point in the middle, it's called stable. That's the saddle, right? So we've got stable, unstable, and saddles depending on the signs of the eigenvalues. Okay, and that's it. That's all that can happen. You can go ahead.
Does the intensity get stronger as you get closer to the origin? Of like the saddle point, like.
Yeah, so these go to 0 faster. The stable ones here, you can imagine like even the -t is getting small really fast. So these things, I guess the way I think about it is, it's like they whip in and then they slow down as they get closer, right? And they whip in and they slow down as they. It's the same thing because with the curve they're following is like this.
Right. Okay.
Right. So as time goes on, they just kind of settle in. So an example of a stable equilibrium in practice looks like, you've seen this one in your physics classes probably. It's like just a pendulum in its resting position, right? Pendulum in the resting position is in a stable equilibrium because if I move it slightly, I return to the same place. If I deviate from this initial condition that put me here, and I start up here, I just return back to the same spot. Yes. Yeah, so I'm going to define equilibrium now because now we're going to take all this stuff. So what I want you to take away from what we've done so far is, if I had a problem and I could write it down with a matrix, then the eigenvalues and eigenvectors would tell me how the solutions behave. Now, the unfortunate reality of science, and engineering, and mathematics is that hardly anything is a problem that you can write down with a matrix. So I'm going to write down the fundamental, but we can always turn it into a matrix by using the derivative. This is what I'm doing right now is every single thing we've learned in the past year all at the same time, basically. So I've got 20 more minutes to teach you everything. All right. It's not on the test, don't worry. This is just like I'm not going to test you guys on this. Maybe a bonus question. Okay, so I'm going to write down something called an example of what are called the Lotka-Volterra equations. Okay, so this equation that I'm going to write down now and that we're going to analyze is related to as one of the fundamental models for studying predator-prey systems. So this one is used all over the place. X prime is equal to x minus xy, and y prime is equal to xy minus y. You can adjust this with coefficients, but what I want you to think here is the x and the y corresponds to like a rabbit and a fox population. I think x would be rabbits and y would be foxes in this case. Okay. So this system is nonlinear. I can't write this down as a matrix multiplication because there's too many x's and y's running around. This is the kind of stuff where this is what models actually look like, even in the very simple cases. So the first thing I need to do is figure out if I've got any hope of trying to analyze this is I should find the equilibrium points. That is, I want to know what are the places where this system doesn't move. What are the values that I can put in? Like the stable spots of a pendulum, right? Pendulum's got 2 stable points. Straight up and down, which is unstable, and straight down, which is stable. I need to be able to identify, to analyze the system, what are all the places where the system will stay at rest. So the way that I do that is I'm going to think of x prime as being a function f of x and y, and y prime as being a function g of x and y. This is the general form of a first-order system of equations. Now, these don't have to be linear anymore. So there don't have to be a matrix involved. And what I'm going to do is I'm going to find all values AB so that f of AB is equal to 0, and also g of AB is equal to 0. Way back when we were doing the second derivative test in 241, we talked about this, right? Finding places where the x derivatives and the y derivatives were equal to 0. So if we do that, this problem, what we'll see is, okay, so I need x minus xy to be equal to 0, and that can only happen when x is 0 or y is 1. And at the same time, I need xy minus y to be equal to 0, which could happen when y is 0 or x is 1. And both those need to be attained at the same time. So if x is 0, x can't be 1. So the only way they could both be 0 simultaneously if x was 0 and also y was 0. So one of the equilibrium points is 0, 0. If there are no rabbits or foxes, then they don't breed. Right? That's like, there's nothing to eat. There's nothing. The other possibility here is y is 1. And if y is 1, y can't be 0, so x must be 1. So the other equilibrium position happens at 1, 1. The interpretation of that is really funny. But the idea would be, I guess, maybe the 1 actually stands for 1,000 here. 1 unit of rabbits and 1 unit of foxes are perfectly balanced, where they eat and breed in just such perfection that the populations never move. Would be the interpretation of that. Or if you like, the pendulum doesn't move when it's pointed straight down. So
It's the 0, 0 is the unstable equilibrium.
I haven't told you if they're stable or unstable yet. I haven't told you anything. We are not yet ready to analyze these things yet because we haven't taken the derivative yet.
Yeah, but you point your clock down.
Well, okay. So what we're looking at now is a picture that looks like this. We have the xy plane. We've got the rabbit-fox plane. And on the rabbit-fox plane, this differential equation appears to have two equilibrium positions, one at 0, 0, and one at 1, 1. And what I would like to do is that simple, dumb analysis that we did for the linear systems, where I look at the eigenvalues and it just tells me how the functions behave around that point. But I don't have a matrix. I need a matrix to do that. I have to have something I can find eigenvalues and eigenvectors of. Fortunately, I can make a matrix. So I don't know if you guys remember the Jacobian matrix, but it's back. So we're going to look at the matrix J, which looks like the derivative of f with respect to x, the derivative of f with respect to y, the derivative of g with respect to x, the derivative. Remember this from the change of variables theorem? Here it is. This is a way of basically turning a nonlinear function into a linear one. And the idea of taking this derivative, I guess in this case we can write down what this is. This is the Jacobian. Things that aren't lines suck, so we replace things that aren't lines with things that are. That's the whole role of the derivative, right? I get rid of a function and replace it with a tangent line. I get rid of a surface and replace it with a tangent plane. I get rid of this matrix thing, this non-matrix function, and I replace it with a matrix function. 1 minus y minus x. This with respect to x is y. This with respect to y is x minus 1. And the idea here is, near each of these points, as long as I keep my scope small enough, near the point 0, 0, near 0, 0, like a little window around 0, 0, that differential equation acts like this. X prime, y prime is approximately equal to j times xy. It's not a linear system, but it's almost one. So I'm going to write down what the derivative is at 0, 0. What is the slope of that system at the point 0, 0? J at 0, 0 is the matrix 1, 0, 0, minus 1. It's probably not hard to figure out what its eigenvalues are. 1 and negative 1. So the idea now is, what we're saying is that near 0, 0, the system looks like x prime y prime is equal to 1, 0, 0 minus 1 xy. In that little window around 0, 0, that's the way the system behaves. And in here, lambda 1 is equal to 1, and v1 is 1, 0, and lambda 2 is minus 1, and v2 is 0, 1. For a little tiny window, this looks like the sort of problem I can analyze with the matrix. What sort of behavior do we have there? Well, let's see. It's going away from 0, 0 on this line, and it's coming into 0, 0 on this one. Oh, I'm just telling you that's what they are. It's basically the identity matrix. Yeah. So locally, near that point, that's the way the solutions behave. So our guess for the behavior in these quadrants is pretty easy. It should look like this. And up here, solution should look like this. And in here, solution should look like this. There's nothing else for them to interact with, right? Near that equilibrium point, the fact that these solutions are being sent away and here they're being pulled in says this kind of behavior should be happening. I haven't written anything down in this quadrant up here yet because there's another equilibrium point, which is also influencing the way the solutions behave. So now I want to figure out, okay, what's going to happen in a little neighborhood of this point? Notice that nothing I've written down so far suggests anything like population, like predator-prey models, right? Like, that's not the way, you don't have like negative rabbits. So let's look at what happens near 1, 1. Near 1, 1, our sort of slope, our linear approximation for the system looks like 0, minus 1, 1, 0. And that says near that point, our system looks like x prime is equal to 0, minus 1, 1, 0. Times, sorry, xy. There's an xy right here. And this has eigenvalues plus or minus I. So what does that mean? What are we doing around the point 1, 1? We're rotating. This says I've got circular behavior. There's no expansion or contraction. There's no spiraling happening because there's no A value, right? Near that point, these things want to move like circles, combinations of sines and cosines. So if you plot this, which I will in a second, what you see is that you get curves that look like this. And the physical interpretation of the answers that you get up there in that quadrant are, as the number of rabbits increase, at some point there's enough rabbits that the foxes start to reproduce more because there's more rabbits for them to eat. So they start eating more, so their population grows. As the foxes population goes up, they eat so many rabbits, the rabbits start to die. So as you're going this direction, that's your rabbit population. So the rabbits die off until there's so few rabbits, the foxes die off, and then you begin again, right? So you end up with this predator-prey cycle. And notice, I could go over to the original problem and turn this into a system and solve it, and I could write down an XT graph, and this is common in papers. There's XT, so this is the rabbits against time, and you're going to get the rabbits are doing something like, well, they started pretty low, and then they grew, and then they collapsed, and then they grew, and then they collapsed, and they grew, and they don't go below 0 because they go extinct if they do that. Right? That tells you how the rabbit population is moving over time. In fact, this model was derived from observing that this is the way rabbit and fox populations worked. Right? That predator-prey models in nature have this property where if there's two populations where one eats the other one, you get this sort of lagging. One of the solutions look like this, and the other one kind of lags it. When this is big, this starts to grow. When it dies off, this starts to die off. And so you end up with the same period, but an offset in the cycle. And that's exactly what is represented in this relationship. So this is what people do with differential equations. This is what it actually looks like in practice for most people. You're very rarely working with specific solutions to differential equations. you are working with a differential equation that you're analyzing with some, okay, we'll get to the question that is probably burning here. You normally do this with numerical analyzers, and the reason that I haven't told you how to solve this differential equation is because I don't know how. Most differential equations don't have solutions. You have to use a computer to generate numerical solutions, and it's a huge pain in the butt. But it's easy to get a computer to give you one of these. This is what most people work with, right? Oh, this is what my system, I've built a model for the scenario that I'm working with. This is what the computer says it chops up based on the initial conditions. I want to make sure I choose initial conditions that are in the right area, and that I understand how I pass from one kind of behavior to a different behavior as I slide those initial conditions around. The fact that there is cyclic behavior here is meaningful if you were doing this kind of analysis of these things. So the very last thing I want to do is show you some examples of some more interesting nonlinear systems, because there's a particular sort of behavior that I find particularly amusing that I'd like you to see as the last thing here, and maybe to convince you to learn how to program these math problems into computers. Thanks, Zoe. Okay, so let's see if I can sort of break here by recording with the output of my computer. All right, so we are looking for, that's too far. I don't want to do that one yet. Let's go up here to the top first. Okay, so this is the model that sorry, not that one, this one. This is a computer picture of the model that I just wrote down. And a computer picture of that model, if you feed it a bunch of, this is the numerical solver yelling at me about like singularities in the solution space. This would be a typical sort of diagram that you might see if you were working on a system in practice. I fed this a bunch of initial conditions. It gave me a slope field. It is basically numerically created contours for this thing that describe the cycles that happen with respect to different initial conditions. And I can look at this and just see, oh, there's different behavior here. I'm swooping in and then leaving, and I'm cycling in here. And of course, the reason is if you go through and you actually calculate, like we did, where the equilibrium points are, you can expressly calculate that they're right here and right here. The equilibrium points dictate that sort of saddle point behavior here and the complex eigenvalues here. So I actually did this because I did the full analysis where I even wrote out the eigenvalues. Okay, so here's another sort of an approach to a different nonlinear system. This is pretty simple, right? There's only quadratic terms here. X prime is equal to x times x minus 1. Y prime is y times x plus y minus 3. And already from this, I'm starting to get suspicious that there's like weird stuff happening, because I look at this and I think something weird is happening here. Those arrows are pointed in opposite directions. Something weird looks like it's happening right there because I have that arrow pointing in and this arrow pointing in sort of like against each other. So, and then there's like this thing, like, I don't know. You know, what does the analysis look like? Oh, this is going to be a great view of a blank screen back there. That's beautiful. Okay, so the first thing I did naively was I'm just going to hit it with a whole bunch of initial conditions and see if I can predict what's happening. This, again, this math in practice, this is what it looks like. I don't know what this is doing. I'm going to hit it with a million initial conditions and see what the curves do. So every one of these curves is generated by selecting a dot, hitting it in the numerical solver, and seeing where the curve went. So I look at that and I think, okay, there's pretty obviously an attracting, like a stable equilibrium point right here. It's sucking everything in. Something weird is happening here because I've got this cross pattern happening, and I still haven't, okay, so out here I kind of understand what's happening. Over here it looks like I've got behavior like this. I don't know what this is. So I created a stream plot, was the next thing. Okay, so this is the computer attempting to come up with what it thinks the solutions to this are. So this is its version of the curves. Okay, so now I got a better idea. Okay, so that is pulling things in for sure, because there's a lot of arrows pointing to that. But there's nothing here. And I've got this weirdness where I've got arrows erupting from nowhere. Like, what the hell is actually happening? So I numerically calculated for the equilibrium points. Notice they're sort of hard to see that they would be there, which is why calculating the equilibrium points is an important step here, not just eyeballing them from a vector stream. And then if you calculate their eigenvalues, you can see exactly the behavior. I have calculated the matrix. I hand calculated the Jacobian matrix. And then I plug in I just took the eigenvalues of that derivative at these places. And what it tells me is at 0, 0, -3 and -1 means two exponentials that are getting smaller, which should be attracting, which it is. At 0, 3, I have one positive and one negative, which should be a saddle point. And you can't see it, but you can see as you come up and down, it looks like it's leaving. But in this direction, it looks like things are being attracted. The eigenvectors for that matrix would tell you that that's what was happening. There'd be two directions that was happening in. Okay, and the last thing I want to show you, which is my favorite, is even knowing the eigenvalues and eigenvectors isn't enough. So this is the first step on the rest of your life.
How'd your computer not crash while doing all this?
I did it on my home computer, and then I saved it all and uploaded it to this one.
Got it.
All right, so now we're going to look at an equation like this. X prime is equal to y, and y prime, I think, is minus x plus x squared minus 1y. And I think this is called the van der Pol equation. It shows up in physical applications. And that's its vector field. So all kinds of stuff is happening there. So then you think, okay, well, this turns out to have a single equilibrium point at 0, 0. That's what the streamlines look like, and that's really suggestive because it looks like what's happening in the middle is we're spiraling out, but and then we're like, okay, so you spiral out, and then you hit this wall that it doesn't look like you get through. Like there's this wall here. And if you're outside, you get pulled into that same wall. That doesn't seem like it's present in the description of the original equation, so I looked at this and I was like, okay, I'm going to plot a couple of curves just to see. And you end up with these guys. So what that's telling you is, I picked an initial condition way out here, and it got pulled into this thing where it's looping around this over and over again forever. And if I started inside, it curls out until it hits that same thing. So this is something that shows up in a lot of applications called a limit cycle. This is a system of differential equations, a nonlinear differential equation, that no matter where you start, you end up not at a single equilibrium point, but at a stable cycle instead, an equilibrium cycle. You're trapped in a behavior that you can't leave. This is often very desirable for an engineered system to have some sort of dynamic but stable behavior happening. So if you start in the center, if you actually do the analysis here on that center point, so we can do that, the eigenvalues are complex, and the real part is positive, which means it's an expanding spiral, an unstable spiral. So you start in the middle, and you spiral away from it. You start anywhere in the middle here, you spiral like this and get further out. So I started here, and you go out, and you end up in the cycle. If I started here, I would spiral out to it's pushing things away. So why is this stuff hard to use in practice? The fact that this exists is not visible there. I can't see that there's this limiting sort of function structure that shows up. That's not part of the eigenvalue analysis. The eigenvector thing tells you if you were near the middle, you get thrown away. It did not tell you if you were outside this thing, you get sucked into it. So this is the beginning of years of work and technique if you end up using differential equations. And it still basically boils down to derivatives and matrices and eigenvalues and eigenvectors. So everything we learned is basically all present in this stuff. So welcome to the rest of it. All right. Tomorrow I posted a couple of mock tests, and tomorrow we'll just go through problems. I'll see you guys. What's that? It is.